to record it again. So the other approach, thinking humanly, based on cognitive modeling. If you are going to say that a given program thinks like a human, we must have some way of determining how humans think. So if you're gonna pick this approach to build AI, you need some sort of actual other requirements. You need to get inside the actual working of human mind. There are three ways to do that, and that create three branches actually of studies. Through interoception, trying to catch our own thought as they go by. You know, like what we do normally, we do that ourselves probably, like to understand what's going on in our head. Through psychological experiments, observing a person in action, and also through brain imaging, which has become more popular these days. But you know, reading signals, giving input, stimulate to the well, for human is probably more difficult, but there are some experiments as well, like getting some information out of brain. You know, I don't know if you have heard or seen. You know, there are these poor monkeys with needles in their brain. They have been trained to give response to the input. I've seen those in Oxford, I think it was, with different inputs. They were observing the signal activity in their brain while and recording that. There are databases for this, and there are studies. I don't remember exactly what university in US was, but also both across Atlantic, people are doing research everywhere around the world. Once we have a sufficiently precise theory of mind, it becomes possible to express the theory as a computer program. Well, one approach, one field of study, people are doing differently in psychology, brain imaging, and neurology as well, and also sort of philosophical approach to understanding the brain with cognitive. The interdisciplinary field of cognitive science brings together computer models from AI and experimental techniques from psychology and construct precise and testable theories of human mind. Cognitive science, however, is necessary based on experimental investigation of actual human or animals. AI and cognitive science continue to fertilize each other, most notably in computer vision, which incorporates neurophysiological evidences into computational model. But as I said, they're growing now as two sort of independent, related but different fields. Okay, thinking rationally. Among those four boxes we had a look at, the other column was based on rational. Okay, thinking rationally is based on laws of thought. So if you want to create something which thinks rationally, first you need to figure out what are laws of thought, how rationality works, right? So to do that, we should go back to you know, Greek philosopher like Aristotle, who was the first person who attempted, well, who was the first person we know, probably before him. Also, people have been working, but the very well-known philosopher who tried to codify right thinking, that is irrefutable reasoning process. So gives you steps of thinking how to get from one point to another point, which is repeatable, which is the same for everyone. So his work gave them, you know, just the patterns of thinking and examples of how this methodology works, and other people also followed him later to build up and expand concept of logic, mathematical logic, and also logic as a field itself. Logicians in 19th century developed a precise notion of statement about all kinds of objects in the world and the relation among them. By 1965, programs existed that could, in principle, solve any solvable problem described in logical notion. So theoretically, we've got somewhere we can describe everything in logic, and we can conclude on everything in logic, theoretically. But the so-called logicist tradition within artificial intelligence hopes to build such a program to create intelligent system. Still not complete. Still, there are a lot of different, aspects need to be taken care of, which we have to be careful. There are two main obstacles to this approach. First is it is not easy to make informal knowledge and state in terms of formal terms and logic. Look around yourself. You see so complicated things, talking about colors, shapes, size, wave, speed, emotions, converting all those to logic, it's not a trivial task. It is very difficult to represent everything in logic, specifically those which are not 100% 0-1 black and white, right? So talking about logic and mapping everything to logic, well, still needs work. I'm not saying it's doable or not doable, but not yet. Second, there is a big difference between solving a problem in principle and solving that problem in practice. Even problems with just a few hundreds facts can exhaust the computational resources of any computer unless you have some sort of guidance to how to find the answer or how to do the reasoning. So even if you be able to model everything, it is really difficult to implement them on our ordinary computers. Aristotle says, what are correct argument thoughts process? So Greek school developed various forms of logic, notions and rules of delivering the thought, may or may not have proceeded to the idea of mechanization. Direct line through mathematics and philosophy to modern AI. I like that. With logic approach, if you want to continue this line, actually you are going from you're trying to go from math to AI. Well, might be able, might not, but I don't think you can do everything with this. Problems, not intelligence behavior, is mediated by logical deliberation. And what is the purpose of thinking? What thought should have? Okay, how you gonna convert that to actions? Okay, my monitor freezed, so I stopped my video. Can you still see me? Can everyone see me?
No.
Oh, no?
No, your video is off.
Okay, I turned the video off because my monitor freezed for a second. I couldn't see changes, so it's okay. Well, probably network is. The problem is I can't see your comments too.
We see the slides and everything fine.
Okay, very good, very good. So very good. All right. So I turned the video on as well, just to make sure that it's not frozen. So we define a creature or a concept called agent. Sorry. Called agent. Agent is just something that acts agent comes from the Latin agere. Although the computer program do something, but the computer agents are expected to do more. So sort of extension to the concept of a program or a simple interactive program. Agent operates autonomously. These are our assumptions. We use concept of agent, in every session. So remember that. Operate autonomously, perceive their environment, persist over a prolonged time period, adapt to changes, and creates and pursues goals. So agent ideally has everything we expect to have an intelligent object. So we try to build that. We focus on agent, specifically on the rational agent, which is the one that acts so as to achieve the best outcome, or when there is uncertainty, to best expected outcome. Okay? So rational agent will be our main focus on the work, which means has these characteristics and can achieve the goal, or in uncertainty achieve the best possible goal in the environment. Making correct inferences is sometimes part of being a rational agent, because one way to act rationally is to reason logically to the conclusion that a given action will achieve one's goal, and then to act on that conclusion. On the other hand, correct inference is not all of the rationality. In some situations, there is no provably correct thing to do, but something must still be done. For example, imagine an insect in an environment looking for food, but doesn't see any food. There is no food in its reach. So logically, while there is no food to go for, but still needs to do something to do that. That's why you see some of them just start moving randomly or doing something to get them closer to the to food, to the goal. There are also ways of acting rationally that cannot be said to involve involve inferences. For example, when your hand gets close to a hot object, you don't think rationally. Actually, you have a reflection, automated reflection. So our agent might need to have sort of that actions as well. So there is a logic, but there are logics above other logics as well. So rational behavior, doing right thing. Rational behavior here, we say doing the right thing. The right thing means that which is expected to maximize the goal achievement given the available information. So right thing means doing the thing which maximizes the goal achievement. Doesn't necessarily involve thinking. Example, blinking reflex, but thinking should be in the service of the rational action. The rational agent approach has two advantages over the other approaches. First, it is more general than laws of thought, because the correct inference is just one of the several possible mechanisms for achieving of law. We are not denying logic, we are not denying reasoning. We have that, but what we think that would be required, but that's not the only thing. Secondly, it's more amenable. It's into scientific development than the other approaches, from human behavior to human thought, or human thought. The standard of rationality is mathematically well defined and completely general, and can be unpacked to generate agent designs that provably achieve the goal. But human behavior, on the other hand, is well adapted to a scientific environment, and it's not as clear as logic and math we have and we can implement. So basically, what we have as a definition of agent from now, agent is an entity that perceives and acts. This course is about designing rational agent. Okay, abstractly, if you want to represent that in an abstract way in scientific language, an agent is a function from perceived histories to action, from what it has got before or the knowledge it has to an action, from perception to action. Okay, this is a agent is a function from your previous information on current and previous information altogether, getting from environment, it makes an action, makes a change into environment, makes a change applied to the environment. For any given class of environments and tasks, we seek agent or class of agents with the best performance. Okay. Computational limitation make the perfect rationally unachievable. So we know that perfect rationality might not be in reach, at least for close future, but we design our agents to be a better, we'll try to improve them better from one from another. Design best program for given machine resources. Any questions so far? All right, so that sort of clears and sets our course setup and assumption. From next week, when I come in, we start talking about agent. What is agent? A rational agent. How to make an agent. What sort of information it gets. What sort of actions it has, and the interaction with environment and the way it behaves rationally. We will focus on that. Before getting there, I want to give you a brief history, actually, to open up again open questions and discussion together to have a better understanding of AI. Okay, very good. The foundation of artificial intelligence. To provide a brief history of the discipline that contributes ideas and techniques to AI, we recognize that the history around a series of questions arising from different interrelating disciplines. Okay, for each discipline, I these are coming from book. I just lay out the questions, fundamental questions we have in that discipline related to AI, and we talk about those questions, and you give me your thoughts and answers. Okay. The areas we are looking into are philosophy, mathematics, economy, neuroscience, psychology, computer, control theory, and linguistic. Okay, philosophy relates to logic, reasoning, mind as a physical system foundation, language, rationality. Mathematics is related to formal representation, proof of algorithm, computation, computability, tractability, probability, and economy, things like utility, decision theory, game theory, neuroscience, but physical substances of the mental activity, neurons, synapses, and brain activities, psychology, phenomena of perception, motor control, experimental techniques, computer, building computers and engineering, control theory, design system that maximize an object function over time, and linguistic knowledge, presentation, grammar, and other related AI-related capabilities. Philosophy. In terms of philosophy, there are major questions related to AI. Question number one, can formal rule be used to draw valid conclusions? So if I only follow formal rules, can I get to right conclusion? How does the mind arise from physical brain? This is a huge question. This is, think about the whole history, the concepts we have from older philosophies, from religions, from supernatural beliefs, from many different things coming in, saying that if you have brain or a collection of material just wired together and to do signal, exchange signals with each other, how do you create mind out of that? The connection of it. This is a big philosophical and fundamental question. Where does knowledge come from? And how does knowledge lead to action? These are basic questions philosophers, who are working related to AI need to answer. Just briefly looking, I kept this card. I want to just go through because there are some keywords, key person in it, and introduce them. And I'll be happy to discuss that as well. So, Descartes was the strong advocate of the power of reasoning in the understanding the world, a philosophy now called rationalism. Okay, and who has even people like Leibniz and Aristotle included in that. So rationalism is actually it's philosophy school belief of having everything in kind of rational related together. However, it was he also believed in something called dualism. So he held that there is a part of the human mind. So this is interesting. He believed that there is a part of human mind. We call it soul or spirit, or part which is not physical, that is out of nature, except from physical laws. He believed that animals, on the other hand, did not possess this dual quality. They could be treated as machines. Ouch. Machine. I don't know. So what do you think? This great. Do you agree with this dualism and rationalism? So which part do you don't like? Animals. Okay, yeah, I don't like. So let's take this off. Okay, so let's say he changed his mind about animals. How about the rest? Do you think rationalism and dualism, works? You have two parts, physical, non-physical. It is a long story, matter of discussion. I agree. So an alternative to dualism was materialism. In materialism, holds that brain operation according to the laws of physics constitute the mind. There's nothing else. It's just matter. It's just brain which works. Well, personally, I don't know. These are philosophy schools, philosophy approaches, and they have big giant people behind each one. So just introducing. And one of the interesting things here is free will. It's simply the way that the perception of available choices appears to be choosing entity. So do you believe in free will? Do you think with brain, if everything is physical, everything is determined by physics, how an AI, if we can build, might have a free will, can decide freely, can just, which is not under effect of physical components. Do you have anything? No? Okay. Long discussion. I wish we had in-person class. We could elaborate on those and talk about that much more. Okay, let's continue. Given a physical mind that manipulates knowledge, the next problem is, so in philosophy, let's say we solve that. We solve the problem of brain and thinking. Okay. The next problem is establish the source of knowledge. Where is knowledge coming from, and how knowledge is handled, and so there is another movement called empiricism that's starting from Francis Bacon and others, which says nothing is in the understanding which was not first in the sense. Means that you only can think and process information which coming from a sense. Well, I don't know, but it's David Hume's and Trait of Human Nature. It says, propose that what is now known as the principle of induction, okay, so that the general rule are acquired by exposure to the repeated association between their elements. Building the work of the Ludwig Wittgenstein and those logic people is called logic positivism. Okay, these are AI-related philosophy discussions. And each of these topics can go for forever. This doctrine holds the knowledge can be characterized by logical theories, connected ultimately on observation sentences of the corresponding sensory input. Thus, logical positivism combines rationalism and empiricism. Well, it's a claim of the book. The confirmation theory of Carnap and Karl Hampel also attempts to analyze the acquisition of the knowledge and experience through senses. All right. So it was probably the first theory of mind as a computational process. So mind as a computational process. See, it looks kind of obvious to us. We compare brain with computer and the process and knowledge. So, but think about that. At a time that no one had any idea, then there was no computer, there was nothing that is similar to that. People were trying to solve this problem, to understand this. And it might be things which we still don't know, haven't seen. In future people might find out and figure out, and they can explain it in a better way. The final element of the philosophy called picture of the mind is the connection between the knowledge and the action. This question is vital as AI becomes intelligent, requires action as well as reasoning. Moreover, only by understanding how actions are justified can we understand how to build the agent whose actions are justifiable. Aristotle argued that actions are justified by logical connection between goals and knowledge of the action outcome. So Aristotle suggests logic, goal. These are connected through logical steps. Okay, mathematics. Let's come out of philosophy and get closer to engineering. In mathematics, there are major questions related to AI. What are the formal rules of the valid conclusion? And what can be computed? And what do we reason with the uncertain information? Uncertain information, okay, formal rules, and computing in mathematics. To deal with these questions in mathematics, we need three fundamental areas: logic, computation, probability. You'll see that, in this course, you see logic, computation, and probability are major parts of math included in AI. The idea of formal logic can be traced back to the philosophers of the ancient Greece again, but its mathematical development early began with the work of George Boole. George Boole, who invented Boolean algebra, which we use in computers. Then Gottfried extended the Boole's logic to include the object and relation, creating first-order logic. This is pure logic, pure mathematics, but it was, created another level, higher level, more complicated way of, understanding and reasoning. Alfred Tarski introduced theory of reference that shows how to relate the objects in a logic to object in the real world. The next step was to determine the limit of what could be done with logic and computation, actually limitations and capabilities of the mathematics. The first non-trivial algorithm, this is a keyword, algorithm we use a lot, thought to be the Euclid algorithm to computing the greatest common divisor. Okay, and Boole and others discussed algorithms for logical deduction, and by the late 19th century, of course, were underway to formalize the general mathematical reasoning. General mathematical reasoning. These days with an algorithm, well, it's impossible to explain computers. It's impossible to explain programs. Algorithm is the way of, step by step going from what we know to what we are looking for, from where we are to the goal. Then a big name, Gödel, showed that limits on deduction do exist. So we said algorithm, how to calculate. Now, someone comes in and says, okay, or although you have mathematical tool, although you know how to do it, but there are certain things that you cannot do, you cannot reach. There are, and he talks about incompleteness theorem. He says that there are things you can't do. Alan Turing, in relation to this, again came in and he talked about computability. Okay, what can you do with computer and what you cannot do with computers? Okay, and there is a thesis called Turing thesis, talks about, and he introduced something called Turing machine. It's a mathematical concept that actually explains how things are calculated stepwise in a machine, in a computational machine. This is basis of computer science. And he introduced the concept of computability and intractability. Means there are things that you cannot reach from point A going to point B. There is no way you can reach there with these steps or with this computer. Cook and Crabb showed the large class of canonical combination search and reasoning problems that call NP complete. This is a keyword. There is a reason I'm introducing this, because in AI, when you review books or probably papers or our discussion, you hear about this NP complete or NP hard. There is something else called NP hard. Okay. These are problems, okay, any problem class to which the class of NP-complete problems can be reduced to is likely to be intractable. So these are class of problems, okay, which are likely to be intractable, which are likely to not to be solvable, okay, so you can solve them most likely. Why I say most likely? Because we still don't know. There is no proof in math, or they haven't been able to show whether they are tractable or not, okay? Although it has not been proved that NP-complete problems are necessarily intractable, most theorists believe they are, okay? They are intractable. Work in AI has helped explain why some instances of NP-complete problems are hard, yet others are easy. And the last but not the least in mathematics is the probability theory. A big deal of this course is related to probability and what we call Bayesian methods. You saw in my introduction to the course that well, it has a big share in AI. Just to give you an example, if there are two boxes, every morning, in front of your door, you get two boxes, box A, box B. First, and you can only take one of them. In one of them, you find 100 bucks. In the other one, there is nothing. Okay, so one of them you find some money. In the other one, you don't find anything. In front of your door every morning. Okay. Let's say first morning you go and pick one of them. All right. So can you go ahead and pick one, A or B? One of them you get money. For the other one you get nothing. Just pick anyone you like. I want to explain something. Class, I want choosing A or B. So Jason goes for B. Maria goes for B. 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 Okay, good. A. All right. So, all right, you pick one of them. All right, and you figure out that the money is in A, not in B. Okay, so people who picked A, they won. People who picked B, they lost. Okay, next day, same thing happens. All right, now it is next day. Which one do you pick? Jason again, B. All right. Nikita goes for A. Nasreen goes for A. Maria, B, A, B, A, and yeah, please, two more, yeah, to see some more people. Okay, very good. Now, you open them, and you see there is money in A, nothing in B. Again, people who picked A won. Next day, which one do you pick? Still keep on picking B, right? It's like a lottery. It's like a gamble. You see, but if you can repeat that for a large number of times, right? If you do that for 1 year, every day you get money in one, you don't get after that. So although it's completely random, although it's completely statistical, but your experience will shape your decision. Do you agree or not? For example, most of the time you have picked A or B, and ideally, half of the time you should get money, and half of the time you shouldn't. All right, but you figure that it's not exactly the same, or it might be different. And in more complex examples, when I have an agent which needs to pick between different solutions, previous experiences will affect your future decision. And that's where this probability thing comes in, okay? So besides logic and computation, the third great contribution of mathematics to AI is the theory of probability. The Italian mathematician first framed the idea of probability for gambling. It served the law in gambling, yeah? In 1654, Pascal, in a letter to Pierre Fermat, showed how to predict the future of unfinished gambling and assign an average. See, try to predict future from previous probabilities. And this became the basis of works. Probability quickly became the invaluable part of all quantitative science, helping deal with uncertain measurements or incomplete theories. Okay, James Bernoulli and Pierre Laplace and others advanced the theory and introduced new statistical methods. and probably the most important person in this area is Bayes, okay? Proposed a rule of updating probabilities in the light of new evidence. See, this is again sort of rationalism, sort of reasoning, right? But in this reasoning, instead of having solid facts, instead of having, well, A and B, I have probability of A, probability of B, and I predict to say, and I'm predicting probability of C. See the combination of these. We call that Bayes rule, and underlies most modern approaches for AI. You will be surprised how these simple probability rules will affect AI and how useful they are in neural network, in all those methods we see later. Economy. I didn't expect that. Economics, right? The major question in economy which might affect AI are how should we make decisions so as to maximize payoff? A pure economy question related to AI. I want to make decision. I remember we had suggestion about intelligence and artificial intelligence. You were talking about decision and maximizing payoff. How should we do this when others may not go along? We're talking about competition and collaboration, okay? Competition and collaboration. I realized that when my monitor is not same. Okay, sorry. There is there is a delay in display. What I'm writing here and display. Sorry about that. So I try to write less. So first one was decisions. Others. And the third one should be for far future. Unfortunately, we still don't know, still are not very familiar, but if you were familiar with very advanced type of machine learning called, which are used in intelligent robotic, reinforcement learning, it's a keyword, reinforcement learning. They are based on this: decision, competition, prediction, and probability. Exactly here. So, brief review, very brief review. I've just picked this from your book just to cover very basic topics. Adam Smith, very famous in one of the giants in economy, was the first to treat it as a science. Using the idea of economies can be thought of consisting of individual agent maximizing their own economic well-being. So AI is sort of closely related to economy now, because in economy, what we're doing is same thing. We're making decision to maximize the benefits, right? Most people think of economy is about money. What do you think? Is economy about money? Is economy about money? Yeah, economy is about money, right? That's what we have learned, right? But economists will say that what they are really is how people make choices, not money. See, it's not about money. Economy, in this approach actually, they say it's about choices that lead to preferred outcomes. Give you an example. It says, look at McDonald's. Okay, going to McDonald's. McDonald's offers a hamburger for $1. You get one hamburger for $1 because they are asserting that they would prefer $1 and customer will prefer the hamburger. You see the point? They're saying that everything is about decision making. It says McDonald's produces one item for $1. These guys, they would prefer to get the dollar, and the customer will prefer to get the hamburger. That's the base of economy. And that's how we include that in AI, right? The mathematical treatment of preferred outcomes is called utility. Was first formalized by Leon Walras, and was improved by Frank Ramsey and later John von Neumann, a mathematician. Oscar Morgenstern, and the book the Theory of Games and Economic Behavior. So we are talking about games and economic behavior. So there is something called decision theory in economy, which combines probability theory with utility theory, provide a formal and complete framework for decision, economy or otherwise, made under uncertainty. That is in case where probabilistic descriptions appropriately capture the decision maker's environment. Okay, decision theory. And decision, well, it works when I have large scale analysis, but when it comes to small scale analysis, it might become even more difficult, because in large scale, what agents do, decision of agents doesn't affect each other. But in a small case, decision of one agent might affect other agents' decision. Let's say if, for example, if you are buying something which is introduced by a very, very big supplier. If I buy one, you buy 10, it doesn't affect each other. You buy 10, I want to buy one, and we both are happy and make our decision based on, well, I have one item, you have 10, I have one utility, you have 10 utility, right? But if you talk about the small supplier, this supplier has only 10 items. You need 10 items, I need one item. Now our decision will affect each other, right? And well, in that case, we have to have an agent which not only do analysis of the environment and the supplier, also needs to make analysis of other agents as well, agents against agents and against system. Okay. Von Neumann and Morgenstern developed the game theory. So it was a theory, and you can well, see that included a surprising result that for some games, a rational agent, this is interesting. In some games, a rational agent should adapt policies that are randomized. This was unexpected. So we're talking about rationalism, being rational, and in small scale, well, in some games, not just scale, in some games based on theory, proved that this agent will make more success or have to pick policies which are randomized. And we include that in AI. For most part, economists do not address the third question listed above, namely, how to make rational decision when payoff from the action are not immediate. Not immediate, but instead a result from several actions. Sorry, my monitor flips. Okay. Results from several actions taken in sequence. This is another very, very important subject in AI as well. So if my agent wants to make a decision one time, it's different if my agent needs to make a chain of decision, one after each other, to get to a goal. And that branches out to many cases. For example, for instance, You want to go from in a square shape environment. Your agent is here. You want your agent to be here, okay? And there are different items on your way with actually the prizes and also or punishments. Your agent goes through, and these items might also move or be just fixed. But your decision at this stage will change your decision at next stage. Because if you go to this square, your next decision either will be this one or that one. But if you go to this square, your decision will be different. So your future decision are function of your previous decision, and you haven't done anything. So you have to predict, like a chess. When you play chess, sorry, each step of decision will affect all your decisions in future. And your agent needs to have all these connected together. To do that, there is a concept called Markov decision process, MDP, Markov decision process. And someone, Richard Bellman, one of the biggest people in this area, and in reinforcement learning, as I said, for robotic AI, has developed a model and explanation how to make an efficient decision or lowest cost decision to reach to the goal through chains of decision. This Markov decision process are just probability-based state transition model. Just briefly, I'll try to talk about that probably at the second half of the course or later part of the course. Any questions so far? Okay, neuroscience. Well, I'm getting close to the end. It will be done soon. In neuroscience, the major question in neuroscience is just how brain process information. How do brain process information? Well, just to give you an idea of how brain is compared with a computer, just look at this. Computational units, storage unit, cycle time, operation, and memory operation, comparing a supercomputer, a personal computer, and human brain. All right, so computational units. First row, you see a supercomputer might have 10,000 CPUs, 10 to the 12 transistors. A personal computer, normal computer like what you have in front of you, might have 4 CPUs, 10 to the 9 transistors. Brain has 10 to the 11 neurons. Storage unit, a supercomputer can store this much of information, 10 to the 14 bits of RAM, 10 to the 11 RAM, and brain again has a 10 to the 11 neurons. Well, memory, the information storage in brain and memory mechanism in brain is partially known, but it's not in detail. We don't know in detail how information are saved in our brain. There are theories, there are explanations, how we access the previous data and memory in our brain, but there is no clear explanation. That's why it says just in the number of neurons. And synapses, actually, the connection between synapses. On average, each neuron in the brain is connected to 1,000 other neurons, which makes 10 to the 14 synapses connected different parts of our brain. And cycle time, it's in the range of gigahertz, or second is 10 to the negative 9 seconds. So each operation, each pulse in supercomputer or in personal computer, it's as fast as 10 to the negative 9 seconds. But in brain, well, it's not like that. It's pulses like this. This is in the range of millisecond, 10 to the negative 3. So individual component of brain of much slower, 1 million times at least slower than individual components in brain. Okay, but operation speed, brain is much more efficient. It doesn't have some other information. I can tell you that for this one you need several kilowatts of power, tens of kilowatts of power. In this one you need at most 30, 40, less than 100, less than 50 kilowatts, less than 30 kilowatts energy. So your brain is super efficient, super fast, super reliable, and with brilliant computational capabilities. Well, and we still don't know how does it work. Still, we don't know how brain process information. So this is probably the biggest question we expect from neuroscientists to tell us how information are processed, how information are saved in brain, how come brain has such a high reliability. Reliability means just we're losing synapses. You know, since I have started my lecture today, you have lost, unfortunately, hundreds of synapses. Hundreds, not because of my lecture, sorry, not because what I say. Naturally, everyone every second loses on average one synapse in our brain. That's why we get older, our brain shrinks, and our mental capability might not be as good as it used to be, right? So naturally, every second since I started this argument till now, on average, each of us, we have lost several synapses. But still works. Still, you don't feel any change, any abrupt change in your capability. But in computer, it's impossible. In computer, if you have 1, 2, 3, random wires, just cut them, your computer will stop working. So it's not that reliable. We still don't know how brain works and has all these capabilities in it. And this is probably the biggest question AI expects from neuroscientists. Well, and while other disciplines, I'm not going in details of those. They are in the book. You will. I'll suggest to go through them and read them. And if you have any discussion or anything you want to bring up in class, please do that. I'll be happy to do that. But while disciplines are psychology, the main question we expect from psychology is how do humans and animals think and act? Very complicated questions. How they think and how they act, how they decide to act. Computer engineers, from computer engineers, we have this big question. How can we build an efficient computer for AI? People are working like every month, every week. I see publication, I think works. People are making better computers for AI, smaller, faster, cheaper, and more flexible computers for AI. Control theory, the question is, how can artifacts operate under their own control? And from linguistic, how does language relate to thought? This is a very, very important question from linguistic and from linguistic people to answer us. Okay, any questions so far? Okay, right. So there are also chronicle history of AI. I just included them in the slide, and they're also in the book. Please go ahead and have a look at those just as a history, similar to discussion I had in class. And well, I hope you like it and you find it interesting. So at the moment, what we have in AI, as you can see, there are many products, many computers around us, many applications, from very small to very large. of AI, and I think they're gonna, continue and expand in almost every aspect of our life. And as you have heard this famous argument of the great physician, who said that AI is threatening humans' future because with the speed they're growing, probably the surface human capabilities, and in close future they take over the human life. Yeah, that's for it. What do you think? The last question. Well, I think I explained this, and I hope you don't have confusion about this. If you do, I will. So the last question, what do you think? AI will take over or not? Not yet, no. Okay. Daniel says no. Is it your hope or is it your belief? I don't see. It's frozen again. Can you hear me?
We can hear you.
Okay. So that's good because my monitor is frozen in front of me. All right. So thank you very much for being in class, and I wish you all the best. Please take care of yourself, your family, and try to stay safe from this pandemic. And I hope to see you next week in class. Is there anything you want to tell me or share with me? I'll be I'll listen to you. Otherwise, thank you very much, everybody, and have a nice weekend.
Thank you.
You too. Thank you.
Thank you.